and welcome to your second video about enzymes. This one is talking about factors that affect enzyme action. Okay, so Cambridge objective. Okay, so the first factor we're going to talk about that affects enzyme action is enzyme concentration. So on your screen, you have the results of an investigation in which different concentrations of catalase solution, which is the enzyme, were added to the same volumes of hydrogen peroxide solution. And if you remember from our last lecture, when you add catalase to the hydrogen peroxide solution, and remember water is added to make sure that everything is at equal volumes, one of the first signs that the reaction is occurring is the release of oxygen gas. And so you see that in the form of bubbles, okay? So concentration was varied by varying the initial volume of extract and then making up with water to a standard volume. I want you to pause the video at this point and really take a minute to examine this graph. I really want you to look at both the y and x axes, what is happening in each of those lines, and then push play for the rest. Okay, so just to throw this out there, I don't know how much we've actually talked about this. So usually when you're calculating slope on a graph or at least in STEM, when we were calculating slope, we were calculating slopes of a straight line. And so in order to determine the gradient of a straight line, you select 2 points, which are at least halfway apart. You draw a right triangle and you calculate the gradient between them. However, you'll be familiar with this if you've had calculus, when you are measuring the slope of a curved line, you have to draw a tangent to the curve, and you need to draw a right angle on the tangent, and then you calculate the gradient using the lengths of the triangle sides x and y. And again, you're gonna set up your problem as rise over run, just like you would on a straight line. Okay, but you need to draw that tangent. So I wanted to throw that out there in case you weren't familiar with that. Okay, so looking at these two graphs, to work out the initial rate for each enzyme concentration, we calculate the slope of the curve 30 seconds after the beginning of the reaction. We talked about this in the last video, but really why you want to do this is because after 30 seconds in the reaction, let's put it this way. 30 seconds and before and earlier is the only time where you can be pretty guaranteed that the rate of reaction is based purely on whatever independent variable you're testing. So in this case, it would be enzyme concentration. Once you get past 30 seconds, then it could be a number of other variables like temperature is being changed or further reactions are happening. So really it's between those, it's that initial reaction that you want to measure. Okay, so 30 seconds is a good place. It would be better even to measure before 30 seconds, but actually doing that in the lab is pretty close to impossible. So we can then plot a second graph showing the initial rate of reaction against enzyme concentration. And when you look at these two graphs, the one on the right where you're plotting initial rate of reaction against concentration, what are you seeing? So again, feel free to pause at this point. I really want you to take a look at this graph and see what you can see. Okay, so hopefully you paused and you looked at it. So really what we're seeing is just what we'd expect, that the higher rate of enzyme concentration that we have, the quicker initial rate of reaction, the more oxygen and you can see here it's per minutes. Okay, so the original graph is in seconds, and then this one they converted it to minutes. So I mean, in these conditions, reaction rate is directly proportional to the enzyme concentration. And this is just what common sense says should happen. The more enzyme is present, the more active sites are available for the substance to slot into. And as long as there are plenty of substrate available, the initial rate of reaction increases linearly with enzyme concentration. And then as you see in all rate of reaction graphs, you would expect to see that those lines would go up, 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 and then they would start to go down. And that's as the reaction is happening, less and less substrate is available. Okay, so this graph shows the results of an investigation in which the amount of catalase was kept constant and the amount of hydrogen peroxide was varied. So in this case, the enzyme is what is controlled and the substrate was increased, okay? So as the substrate concentration increases, the initial rate of reaction also increases. And again, this is exactly what we would expect. The more substrate molecules there are, the more there are to bind with for the enzyme, right? However, if we kept increasing the substrate concentration and we kept the enzyme concentration the same, there comes a point where every enzyme active site would be working continuously. And even if you added more, the enzyme could not work faster. So the substrate molecules are effectively queuing up for an active site to become vacant. The enzyme is working at its maximum possible rate, and this is known as Vmax. And V stands for velocity. Okay, so at that point, the enzyme becomes the limiting agent in this chemical reaction. Okay, so temperature on enzyme activity. So this curve shows how the rate of a typical enzyme catalyzed reaction varies with temperature. And we know a lot about this already, okay? So at low temperatures, the reaction takes place very slowly. And that's because the molecules are moving slowly, and so they're colliding less often. They don't have as much energy when they are colliding. And so binding between the substrate and the enzyme is more of a rare event. But as the temperature rises, the enzyme and the substrate molecules move faster, collisions happen more frequently, and they have more energy when they do collide. So then the substrate molecules enter the active site more often. And more often, like I just said, they have more energy. And so this makes it easier for bonds to be formed or broken so that the reaction can occur. Okay, and so we know, and you should remember from STEM, that the temperature at which an enzyme catalyzes a reaction at the maximum rate is called the optimum temperature. Okay, pH and enzyme activity. So this shows how the activity of an enzyme is affected by pH. Most enzymes work fastest at a pH of somewhere around 7, so generally fairly neutral conditions. Again, pause and take a look at these graphics, okay? You can see that enzymes will have an optimum pH, okay? And at the optimum pH is where they are going to do their best work, their fastest work, okay? pH is a measure of the concentration of hydrogen ions in a solution. The lower the pH, the higher the hydrogen ion concentration. Hydrogen ions can interact with the R groups of amino acids. So, for example, by affecting ionization, which is the negative or positive charge of the groups. So this affects the ionic bonding between the groups, which in turn affects the three-dimensional arrangement of the enzyme molecule. And the shape of the active site may change, and therefore reduce the chances of the substrate molecule fitting into it. And a pH is very different from the optimum pH, can cause denaturation of an enzyme. And actually, that's how a lot of poisons work, is they cause denaturation of an enzyme, and so that it is unable to function as it's supposed to. Okay, so enzyme inhibitors, it is possible for some other molecule to bind to an enzyme active site if it is very similar in shape to the enzyme substrate. This would then inhibit the enzyme's function. Inhibitors are chemicals that reduce the rate of enzymic reactions. They're usually specific and they work at very low concentrations. They block the enzyme, but they do not usually destroy it. So many drugs and poisons are inhibitors of enzymes in the nervous system, like I mentioned. Okay, competitive reversible inhibition. If an inhibitor molecule binds only briefly to the site, there is competition between it and the substrate for the site. If there is much more of the substrate present than the inhibitor, substrate molecules can easily bind to the active site in the usual way, and so the enzyme's function is pretty much unaffected. But if the concentration of the inhibitor rises or the substrate falls, it becomes less and less likely that the substrate will collide with an empty site. The enzyme's function is then inhibited. And this is therefore known as competitive inhibition. And it is said to be reversible because it can be, reversed by increasing the concentration of the substrate or decreasing the concentration of the inhibitor. So it makes total sense if you think about it. If an inhibitor if there are more inhibitors than there are substrate, it is more likely that inhibitor is going to bind with that active site, and vice versa. If there are more substrates, it's more likely that the enzyme, is going to bind with the substrate. So it is a reversible thing. However, it still is competitive, and therefore it is called competitive reversible inhibition. Okay, so here is a model of that. So the substrate fits precisely into the enzyme's active site. The competitive inhibitor has a similar shape to the substrate and fits into the enzyme's active site. And so this is competitive, where the substrate and the competitive inhibitor are, they're not actually competing, right? It's all random movement. What happens is that the competitive inhibitor decreases the chances that it's going to be a substrate that's fitting in. And so that's why it's called competitive inhibition. And then in non-competitive inhibition, that's where other molecules may bind elsewhere on the enzyme, which could distort its active site. Okay. And while the inhibitor in a non-competitive reversible inhibition is bound to the enzyme, it can disrupt the normal arrangement of hydrogen bonds and hydrophobic interactions, holding the enzyme molecule in its three-dimensional shape. And the resulting distortion could affect the entire molecule, including its active site, and it could make the enzyme unsuitable for the substrate. So while the inhibitor is attached to the enzyme's function is blocked, no matter how much substrate is present. So this is an example of non-competitive inhibition. Okay, so here's a model of that. Again, there's non-competitive and competitive inhibition. And these are really intuitive names for really intuitive processes. Okay, non-competitive is where the active site is not being taken up. It's not from that. It's from another inhibition changing the shape of the enzyme, which just happens to change the active site, making it so that substrates can't hook up with the enzyme. And then where competitive inhibition is actually another molecule that is connecting to the active site. Okay, so inhibitors affecting reaction rates. So if you look at this model, the red line represents a reaction with no inhibitor. Okay, so the graph levels off because all of the active sites are occupied with the substrate. Okay, the orange line shows a reaction with a competitive inhibitor. This is a gradual increase in reaction rate because the competitive inhibitors are occupying some of the enzyme active sites and not all of them. So as substrate concentration increases, the substrate molecules outnumber the inhibitor and the reaction rate will eventually reach its maximum. And then the green line represents the reaction with a non-competitive inhibitor. Most enzyme molecules have become inactive, but some are unaffected by the inhibitor, so the reaction can still occur, but the rate remains low. An increase in substrate concentration does not increase reaction rate. Okay, so the end product or feedback inhibition. Another way a metabolic pathway can be controlled is by feedback inhibition. So this is when the end product in a metabolic pathway binds to an enzyme at the start. This process stops the metabolic pathway until the end product concentration decreases. Okay, the higher the concentration of the end product, the quicker the metabolic pathway stops. So if you think about poisons, like snake bite or plant alkaloids and nerve gases do this. And medicines like antibiotics, sedatives, stimulants, etc., do the same way. Okay, so I know that that can be kind of confusing, and really the best way to think about it is to see a model. Okay, so let me get my pen. Okay, so here, this whole thing, this whole model represents feedback inhibition. And if you look, we're going to start right here. Okay, so here is substrate number 1. Okay, actually, it's substrate, just substrate 0. Okay, ground 0. So substrate binds here. Now we know this is called the active site, but what is this? This is called an allosteric site. Now, an allosteric site is a non-active site, and when a product binds with the allosteric site, it causes a conformational change in the enzyme and its active site. So when something binds here, it changes the shape of the active site and doesn't allow a substrate to bind to it. And so the point of that is like, yeah, that can happen in poisons when we're poisoned and with medicine, but that also is a cell's own way, our biology's own way of saying, okay, we have enough end product, close down the enzymes for a bit. Okay, close down those active sites so that they're not going to be speeding up this reaction. We have enough of what we need. Okay, so this is kind of like a check for the cell, this allosteric site. Okay, so the substrate binds with the active site of this enzyme. Okay, and it creates a product. Okay, so here it's binding, here's the allosteric site, and it creates a product. Here is the product. Okay, that product is also a substrate. Okay, just so happens to be a substrate. And that substrate finds its enzyme, okay, enzyme 2, and it binds with the enzyme, okay? And you notice that there's no allosteric site on these enzymes, okay? So they bind, and it creates a different product, okay? And this product also happens to be a substrate, okay, substrate 2, and it bumps around until it finds its perfect match, its enzyme, number 3 here, it binds, and it creates this end product here. Okay, this product bounces around, and eventually hooks up to an allosteric site, the allosteric site of enzyme 1. Okay, so when it comes up here, bounces in, okay, it blocks it, it changes the shape of the active site, and now this original substrate can no longer bind with the enzyme. Okay, and that is called a feedback inhibition, and therefore the pathway shuts down. Okay, so factors that affect enzyme action. We've talked about those. Now let's talk about comparing enzyme affinities. There is an enormous variation in the speed at which different enzymes work. A typical enzyme molecule can convert around 1,000 substrate molecules into product per second. And this is known as the turnover rate. So one of the key steps towards understanding how well an enzyme performs is to measure the theoretical maximum rate, the Vmax, of the reaction it catalyzes. Okay, so at Vmax, all the enzyme molecules are bound to substrate molecules and the enzyme is saturated with substrate. Okay, so Vmax. The reaction rate is measured at different substrate concentrations while keeping the enzyme concentration constant. So as substrate concentration is increased, reaction rate rises until the reaction reaches its maximum rate, or its Vmax, okay? So with your shoulder partner, when we get into class, I'm going to have you read pages 71 through 73, which is 62 of 64 of the PDF, starting with comparing enzyme affinities and stopping at mobilizing enzymes. I'm going to have you fill out a table and answer questions in box 38A. Okay. Okay. Enzymes have an enormous range of commercial applications. So they're used in medicine, food technology, and industrial processing. So not just in our bodies, okay? We take advantage of them on a commercial level. And enzymes are expensive. Maintaining them, creating them, expensive. No company wants to keep buying them over and over again if it can recycle them in some way. And so one of the best ways of keeping costs down in these commercial uses is to use immobilized enzymes. And this stuff is so cool. So here's an example. The enzyme lactase, right? So we know that's an enzyme because it has ase on the end, and we know it has to do with milk because it's that lact, right? Lactase can be immobilized using an alginate bead. So milk is allowed to run through a column of lactase-containing beads. The lactase hydrolyzes the lactose in the milk to glucose and galactose. So what does hydrolysis mean? Okay, think about that. We've talked about what type of reaction that is. So the lactase hydrolyzes the lactose in the milk to glucose and galactose. The milk is therefore lactose-free and can be used to make lactose-free dairy products for people who cannot digest lactose. Okay, so the enzyme is run over beads, lactase-containing beads. The lactase goes through a chemical reaction, okay, in which the milk is then separated, the lactose in the milk is separated into glucose and galactose, okay, and we should know how that happens. The milk is therefore lactose-free and then can be used for lactose-free dairy products. Okay, here is an example of that. I encourage you to pause and look at this. Okay, so we're also in class with your shoulder partner. You're going to go to page 73 of the text and discuss the advantages of immobilizing enzymes compared to enzymes in free solution. Okay, and that is all. We will see you in class.